do real simple ones where it's a 1-to-1. Okay, so let's look at this next one. This next one also has 2 H's and just 1 OH. This time we're solving for volume. So it says how many milliliters. And the answer is 7.5 milliliters, but I wanted to show you guys the work. So if we have volume of A, we need the moles of A, or acid, on the bottom. So 2.0 times 2, because we have 2 H's. And then on the top, we're going to go 30 milliliters times 1, concentration of 1 molar. We can see the molarities cancel out. Then we just do 30 times 1 divided by 2 divided by 2, we get 7.5. So that's how that one works. And then this one, we have 2 on the hydroxide side. So that's going to be, but we want to know the volume of our base. So we're going to put 0.1 on the bottom and times 2 for the 2 hydroxides, and then 25 on the top, and then 0.5 molarity on the top. So our molarities cancel, and then we just take 25 times 0.5 divided by 0.1, and then divide it again by 2. Or you can multiply these together and then divide. Okay, here the PowerPoint talks about a titration partner activity. We didn't do that. But let's go on to the pH scale. And this is missing. This is where we're missing a couple of things. So hopefully everyone will go through this video. So the power of hydronium. So what does pH really mean? So it's the easiest this pH scale is an easy method for comparing the strengths of acids and bases. We can test our fish tanks at home. If you guys have fish pee out ammonia, which is a base. It brings the pH up. Our lawns, acid rain brings the pH of the soil down. And even food is pH tested to make sure it falls within the right range. And actually, just a little personal experience here, I made some handmade or homemade shampoo soap. And my sister tried it out, and when she tried it, it got in her eyes and it stung really, really bad because it wasn't pH. Soaps are usually, they put stuff in them so that the pH is nice, about 7. But mine was kind of basic, and so it made her eyes sting. So what is pH? What does it mean, and how is it measured? So we're going to start out talking about water. Water breaks up very slightly, just by itself, to form just a few hydrogen and a few hydroxide ions. So every 1 times 10 to the minus 7th, very small number, of these will separate. And so that's where we get the pH of 7. What we do is we take the negative log of the concentration. So here it's 1 times 10 to the minus 7. So if you guys go negative log in your calculator and then put 1 times 10 to the minus 7, you're going to get the number 7. And that's what I failed to put in here. So, and it's not hard. I know you think of logs and that as being difficult because it's sort of math related, but it really isn't hard. Here is a scale. On this side, we're looking at the hydronium or hydrogen ion concentration. So down here, that's a high number. This is really, really low. So that's 10 to the minus 1, or 0.1. And then this is 0.00000, 14 zeros. Okay, so lots of hydrogen ions, very little hydrogen ions. Then over here, we have lots of hydroxide ions. And then, very little hydroxide ions, and then a lot of hydroxide ions. So this is the basic, these are basic solutions, these are acidic. And then 7 is neutral, because water is neutral. Okay, so pH of between 0 and 7 is acid, or acidic. pH of 7 is neutral. And then if you go from 7 to 14, that's a base. So the concentration, if you have 10 to the minus 1, the pH is 1, and that's a very strong acid. Again, if you punch in negative log 10 to the minus 1, you're going to get 1. Okay, same thing if you do here for 2. So 2 and 3. The pH scale is logarithmic, just like the seismic scale, which we've all experienced in the last month with our earthquakes. So each change of a single pH unit signifies 10-fold change in concentration. So the pH is 10 times greater in a solution of 5 than it would be in a solution of 6. So here are some examples and questions that they go through. I'm just going to go through a couple of them. So a solution with pH 3 is 10 times more acidic than a solution of 4. And that's because as you go down the scale, it gets more acidic and more hydrogen ions. Let's jump to C. If you have a pH of 2 and you've got 10,000 times greater, so 3, 4, 5, 6. So if you move the decimal over, then you're going to get 6. And then 12 and 1. So hopefully those make sense. Some alternative theories. You've got your Arrhenius acids and bases, but they don't include everything. Arrhenius acids they give away hydrogen ions in solution. Bases, hydroxide. And they make negative. But in Bronsted-Lowry, this is an alternative theory. Acids are proton donors, and they give away protons. Bases are protons acceptors. So really the only change from here to here is the fact that we're not talking about hydroxide. And the reason this is important is because NH3 accepts a hydrogen to make NH4, and this is a base. But it doesn't look like a base because it doesn't have hydroxide in it. And so this is one that doesn't fit in this definition, but does fit in our Bronsted-Lowry. So this one we just talked about proton donors and proton acceptors. Okay, another thing we need to discuss is acid-base pairs. In each reaction we have a conjugate acid-base pair, and that's because acid-base reactions oftentimes are at equilibrium, and so they go back and forth. So they're a dynamic or reversible reaction. So let's look at these and see if we can figure out how to do conjugate acids and bases. So what you're doing is you're watching where the hydrogen goes. Okay, so here we have HCl, and we know it's an acid because the H is in front, and so this one has to be the base. So if you can figure out one, then you can figure out the other. So we're going to follow the chlorine, because the hydrogen's the one that's going to leave. So if we follow the chlorine over here, the chlorine gives away, okay, so it gives away as it goes this way, but if you went this way, it would gain. And so if you go to the right, it's a proton donor, which is an acid, but if you go to the left, it's what we call the conjugate base. Because here, if you go from chlorine and you take a hydrogen and end up over here, then you're acting as a base. So there's the acid, there's its conjugate base, and then this one's the base, and you can see as we go across, it accepts a hydrogen going to the right, and it releases a hydrogen going to the left. So that's the base, and that's its conjugate acid. Okay, let's do some examples, and hopefully that'll help. So you have only one acid and one base per side. The one that gains is the conjugate acid. The one that loses is the conjugate base. So if you look at it going backwards, going forwards, if it loses, then this is the conjugate base. If this gains, this is the conjugate acid. So if we're looking at these, oftentimes they'll be hydroxide, so you can tell what the base is. But in this case, you've got an acid in the front here. So water is actually acting as the acid, and then ammonia is the base. Just memorize that ammonia is a base. It'll make life easier. So if we go here and we look at what happens to the N H3 gains. So it gains this way, so that means this is the conjugate acid going backwards. And then this is the acid here, and this is going to be its conjugate base. Okay? The next one is water, which is kind of interesting. You just pick. One's an acid, one's a base, because one is going to give away. So on this one, we'll just say that it's here. So this one takes hydrogen. So that's the base, is it's going across here. If it comes back, it's the acid. And then this is the acid, and it gives away, going to the right. It takes it, going to the left. So base, acid, conjugate base. Oh, last page, yay. Hopefully this isn't too long. So here we have another one, H in front, that's acetic acid. So water in this case is acting as a base. So you know that because if you look at this C2H3, what happens when it gets over here, it loses as it goes to the right. So that's an acid. This base gains as it goes to the right. And that means when you come back, it does the opposite. So this is the acid here, that's the conjugate base. This is the base here, and this will be the conjugate acid. Okay, the rest of those are just practicing. This is a good one to think about it. Bronsted-Lowry acid loses a hydrogen in the reaction. A Bronsted-Lowry base gains a hydrogen in the reaction. Alrighty. If you guys have any other questions, I'm going to have another review, probably a review / assignment / notes, and I'll do a video. So look for that, and please, if you have questions, let me know. Did this not record?